Hi, I wanted to go over problems like this one that might show up on the Khan Academy. You might luck out and not get a question like this, but if you do, I wanted to go over it because it's kind of tricky. So in a situation like this one, what we have is a collision. And so this ball is approaching the rod with a speed v, and it collides with the rod, which is stationary. And then after the collision, the rod rotates and the ball reflects back at a lesser speed than it was moving before. And so our goal is to figure out the angular velocity omega of the rod after the collision. We know the rotational inertia of the rod is I, we know the length of the rod, the mass of the ball, and the initial and final speeds. Okay, so there is this pin here. We have a pin. And remember, when we're looking at what's conserved, a pin prevents an object from sliding, but doesn't prevent it from spinning. So because of this pin here, let me see if I can draw on this. Because of the pin, the total, let's try this. Because of the pin, linear momentum here is not conserved. However, that pin does not, so I can't use linear momentum to solve this problem, but the pin does not prevent angular momentum from being conserved. So we can say the total angular momentum before the collision equals the total angular momentum after. So there's the rod and there's the ball. So that means that the angular momentum of the rod before the collision plus the angular momentum of the ball before the collision equals LR2 plus the angular momentum of the ball after the collision. Okay, so let's look and see if there's anything we can cross out. So before the collision, the rod isn't spinning. And so L of the rod at time 1 is 0. The ball isn't spinning, but remember, since it's going to make the rod spin, we're going to say that it has angular momentum at time 1 equal to R mv sine theta. Okay, moving on to side 2, after the collision, we do have angular momentum of the rod, and we also have the ball moving in a straight line again, so these both stick around. Now let's use the right-hand rule to determine which is positive and which is negative. The rod is rotating counterclockwise, so that's positive. The ball is moving the other direction, and so its angular momentum is negative. So this actually becomes I rod omega rod final minus R M V sine theta for after. Now a couple things here, because right now these look the same. This is before and this is after. So this is V1 and this is V2. So let's talk about this theta here. Theta is 90 degrees in both cases. The instant before the collision happens and the instant immediately after. Both of these thetas are going to be equal to 90 degrees. And so since sine of 90 is 1, they basically just go away. And so what I'm left with here, and R for both of them is this distance D from the pivot to where the collision happens. V1 is given, it's V. V2 is given, it's 3V over 4. So I'm going to go ahead and start plugging in. So D mv, and sine 90 is 1, equals, the rotational inertia of the rod is just called I. Omega for the rod is what we're looking for. That's what we're looking for. And this is minus D m. Now the V at time 2 is 3V over 4. And then again, sine 90 is 1. All right, so we're getting close now. Our goal is to get to get omega by itself. So this becomes 3/4 dmv. So I'm going to add this to both sides. Well, 1 plus 3/4 is 7/4. All right, and the last thing we got to do is get omega by itself. So we're going to divide both sides by I. So that means omega equals 7 dmv over 4I. Hooray! The whole time I was like, uh-oh, what if it's not there? Now I do want to point out that A and B here are pretty similar, right? The only difference is the direction. So since it tells us the counterclockwise is positive, and since we can see from the image that it does rotate counterclockwise, it will be solution A, which you won't let me choose, but I swear that's it. All right. Let me know if you have any questions.